going to give a short introduction. So our next talk is by Christos Masouros, who's a full professor at UCL. So Christos has been working on several topics related to signal processing for wireless communications. And the past few years, he's been working on this topic of joint communication and sensing, or joint communication and radar sensing. And yeah, so we hope that he's going to give us a different perspective now, more a signal processing perspective. And yeah, we look forward to your talk. So please.
Okay, thanks a lot, and I'd like to also start by thanking the organizers for inviting me, and I appreciate the opportunity to talk a little bit about the potentials of this integration. So I actually removed some of my introductory slides because Michelle did a great job to introduce the topic. I just wanted to highlight. So I forgot to say, I'm going to talk about this not from the information theory perspective, but from a signaling design, let's say, perspective. So just to motivate this a little bit, I just wanted to highlight the benefits, the main gains from moving from the coexistence of the two systems, which is the traditional approach when we started thinking about the radar and communication systems together, to this concept of this dual functional transmitter, dual functional base station. So where before you had to deal with interference and the two systems would have to compete for resources, spectrum, power, and so on. Now you have a system that, let's say a super transmitter that does both things at the same time. And this has a number of gains. Obviously, you have one device instead of two, one system instead of two. That's hardware efficient, that's power efficient. So it consumes less power and it's cost efficient. But there are some benefits beyond that, where once you now co-design the two systems, you can mutually benefit. You can trade off performance as we saw, and you can also use one system to benefit the operation of the other. So the sensing to benefit the preparation of communications, and the communications bit to assist sensing. And one future kind of vision I see in this is, once we have, let's say, access points that can do two things, sensing and communications, and if you imagine the deployed 5G infrastructure where access points are on lampposts and buildings, walls of buildings, you can now have a wireless infrastructure that's not only doing communications but smart city sensing, and then have this radar operation as a commodity. And radar operations becoming, a common thing for smart city sensing. Now, in terms of the signaling approaches, so there's three main categories of what I call DFRC, so dual functional radar and communication technologies. And you can find more details at this overview paper and at the bottom of the slide. So the first, let's say, approach is what we call the radar-centric design, where the principle is shown over here. So you have a radar waveform that's designed for radar-only operation. It has a good radar performance, and you try to somehow modulate information on that waveform. And then you have a waveform that does two things. So good radar performance while carrying some information. And there's a number of techniques in this category. The very first, what we think now is the very first approach to integrated sensing and communications is that of pulse interval modulation in the 1960s, where basically information was encoded in the pulse intervals, as the name says, so the on and off of the radar pulse. You can also do signaling over the radar side lobes. And there's techniques where you use the side lobe levels and the side lobe signal strength to convey information, or more general index modulation based techniques. An example of that for MIMO radar would be encoding information on the antenna you use or the frequency you use. So those of you who are familiar with spatial modulation, for example, you can use these kind of techniques to encode information onto an ideal, let's say, radar waveform. On the other hand, you have the communication-centric design, and again, there's plenty of works in this area too, where you have a typical communication waveform, could be an OFDM waveform or a standards relevant waveform, and you use that waveform as it is to try to do match filtering and do radar detection with it and extract parameter information, so track targets and their parameters. And there are some communication waveforms and resources that are actually very good. They have very good radar properties, such as the pilot signaling and pseudo noise sequences that are often employed there, or synchronization signaling, where you can do some limited radar operation and track parameters and targets. And as I said, there's plenty of techniques there based on OFDM or based on Wi-Fi standards and so on. So there's one main benefit of these families of techniques and one main drawback, I think, for both these families of techniques. So the main benefit is you have minimal changes in the classical signaling and waveforms. So you can take a radar waveform, modulate information with minimal changes, and you don't need to change, let's say, the standard or the no major changes in the operation of the system, and get some actual data rate out of it. You can do the same with communications and get some radar performance out of it. Now the one limitation is, I think it's intuitive. So radar waveforms are not designed for communications, and communication waveforms are not designed for sensing and radar operation. So there's limits to what you can achieve in terms of communication performance from a radar signal. Through index modulation, for example, they typically have limited communication rates. And there's limits in what you can achieve in terms of radar functionality from a classical communication waveform. So they're typically difficult to tune. If you want to improve the radar operation, you probably need to use more frames, more resources, and it's in general difficult to tune this performance. And this is why we think this new category of techniques is interesting. So a jointly optimized waveform. I mean, I keep saying waveform, but what we actually optimize is the transmit signal here at the baseband. So you have, in this case of the jointly optimized design, you can design a signaling, let's say, strategy from the start, and that means you can, first of all, you can accommodate both operations from the start and start thinking about both radar and communications from the start, but also you can design flexible trade-offs between them. So as I said, previous approaches are difficult to tune, but now you have an optimized design where you can move from all the way from fully radar, let's say, oriented performance to full communications performance and anywhere in between. And again, within this, you can have what we call radar-centric joint design, where you basically try to design a new waveform that is close to some good radar waveform, or pure weighted optimization, where you directly optimize metrics of the different systems, and many others. So as I said, this, the main benefit I see for this type of signaling is that you co-design the two systems from the start. That means you have flexible use of the resources, time, frequency, spatial resources, and you have these scalable trade-offs where by tuning the signaling that you design, you can go from all the way from 100% radar to 100% communications performance and all the way in between. So that means you can achieve high data rates when you need to, you can achieve high radar reliability when you need to, and you can trade these off, and we'll see some examples in a minute. That also means that you can design these signaling and waveforms to be hardware informed, borrowing the number of techniques that we have already in the comms only literature. And you can make these signaling techniques friendly to low specification hardware, for example. So aside of this motivation, I hope I'll have the time to discuss three technical highlights. So one related to this weighted optimization. Second being the security issues for this DFRC technology, which I think are unique. And the third, if I have the time, is give you a more of a use case scenario where through the DFRC, we have a sensing assisted communication system. So first with the weighted optimization. So here's an example. So again, we have the scenario where with a single antenna array, a single base station, we want to communicate to a number of users while at the same time detecting a target. And we want to do this through a common signal X over here. And our communication signal is going to be this formulation here, where X is what we want to design, H is the channel, Z is the noise. And anything that lives inside h times x, aside of the information signal, we can define as the multi-user interference between these guys over here. And that will give us, it's an example communication metric that we can use. So using this communication metric, we can formulate a weighted optimization. And here's one example of the many that you can think of, where you have a weighted minimization of this MUI, the multi-user interference. And here we have the proximity of the designed waveform to an ideal radar waveform. So you can take any good radar waveform in the baseband domain and try to approximate that to achieve a good radar performance. And the important thing here, and for example, here we have a power constraint, a classical constraint here. The important bit is that here you have a weighted optimization, and the weighting factor rho here is from 0 to 1. And that gives you a priority to the communications or the radar or anywhere in between. So a low value of rho over here, so let's say rho 0 eliminates this factor, and you're focusing only on the radar performance. Rho equals 1 eliminates this factor, and you focus only on the communication performance. Rho between 0 and 1 will give different priority to each of these operations. And you can do a number of variations. As I said, you can include different constraints. So here we have a constraint which is per antenna power. You can have constant modulus constraints. You can incorporate stuff like few bit ADCs or hybrid precoding. You can also take this one step further. Instead of trying to approach a good radar waveform, just incorporate a bottom line radar metric, for example, over here, like the Kramer-Rao bound, which we've also done in recent work. Now, a couple of very indicative results on this trade-off. So first, we look at the communication-only performance, symbol error rate versus the SNR. There's a number of graphs, lines here, but the important ones is our first benchmark is the black line over here, which is the communication-only performance with 0 interference, so the best we can achieve. Here we have a couple of lines from a naive, let's say, benchmark, a closed form benchmark. And this is what you can achieve with this weighted optimization with the two approaches, one the total power constraint and one the per antenna power constraint. And you can see that while at the same time accommodating a radar operation, we can achieve between 1 or 2 dB from the ideal communication performance. Now, I forgot to say that this is results that we take with rho equals 0.2, and that gives priority to the radar operation, if you noticed before. So giving priority to the radar operation, we can still achieve very close to the best, let's say, that we can do for communications. What about the radar performance? So here we measure the beam pattern quality for the different angles, and we have two cases. Where one case where we're focusing on radar detection, where you typically use an omnidirectional waveform to scan the horizon and detect targets, and one where we're focusing on tracking, where you want to point beams to the different directions where you detected that target and you want to track its parameters. So the omnidirectional waveform, the ideal case is this blue line over here, and what we achieve with this weighted optimization is this yellow and green lines, so within, let's say, 1 dB from the optimal. And a similar trend we can see for the directional beam with tracking 3 targets. So the red light over here gives you the radar only beam pattern, so X0. And what we can actually achieve is the blue line with this weighted optimization, so a close proximity to the ideal waveform. A couple of results that directly show the trade-off between the two functionalities, so directly, one against the other. So here we have, first one focuses on, again, the target detection with the omnidirectional beam pattern. And we show the probability of detection for the radar against the rate per hertz per user. And here's where you can very clearly see the trade-off between the two. So this case represents rho equals 0, in which case we have radar only performance or radar priority. And you can see here you have a very good radar performance, but at the same time a non-zero communication rate through this joint signaling. And this is what you get with rho equals 1, where you have the priority, full priority on communications, but still achieving some sort of radar reliability. And by tuning row, you can get all these points in between. And this is, I think the big benefit with these kind of jointly optimized designs. And here's what happens once you start making your system more symmetric. So you increase the degrees of freedom versus the number of users you need to serve. So this is with reducing number of users. And you can see that when the system is less symmetric, so more antennas, a higher ratio of antennas to users, this trade-off becomes more benign. Oops, sorry. So you can achieve better rates with a minimal sacrifice in the radar performance. A similar trend here, where we plot in the tracking stage the mean square error with the achievable rate. And again, you can see the trade-off that as I increase my communication priority and increase my achievable rate, I tend to have a sacrifice in terms of the estimation, so the MSC of the radar operation. And again, this trade-off becomes more benign as I have more degrees of freedom to accommodate this. And just to convince ourselves that this is not just a theoretical concept, we've recently been doing some experiments in our lab in UCL where we try to emulate some sort of dual functional transmission where we have an array of antennas. We emulate two communication users, and we try to measure the radar beam using this receive antenna, trying to measure the signal strength in this absorbent material to get an idea, let's say, of how well we're doing in terms of creating a beam for the radar operation. And we've been able to observe signal constellations for the communication operation and theoretical beams, and also measure them in practice. And you can see as we tune this weighting coefficient, you can get from a comms only performance or a comms priority, where you have nice clean constellations, but no real beam forming for the radar, to a radar priority where you have a good radar beam, but a very messy constellation. And we've been able to actually measure that beam and also measure the performance in terms of the communication bit error rate. Now, the other bit I'd like to discuss about is the security issues related with DFRC, which I think they have some uniquenesses in this DFRC scenario. So now if we imagine again the same concept where we have an access point trying to communicate to users while detecting a target, now your radar probing signal carries useful information that is intended to the communication users. So that opens up the possibility of a target, when it's a malicious target, to extract or eavesdrop some information. So the target could be a friendly target, could be a non-cooperative target, let's say a non-cooperative car, but it also could be a malicious UAV or an enemy aircraft in military scenarios. So you want to come up with ways to make sure that the information here that you transmit to these guys is safe from eavesdropping from the target. And you also want to have some sort of physical layer solution, because even if the data is encrypted, the fact that you're transmitting can actually be useful information to, let's say, an enemy target. So you want to protect the transmission from being eavesdropped. And there's the good news is that there's many physical layer security solutions that we can borrow from the communications only literature. But I think there are some interesting conflicts here in terms of the scenario. So if you look at, again, at the scenario, so the radar link in particular, I think it's quite interesting, where on one hand, you want to send power to illuminate the target, so send power towards the direction of the target to achieve a certain radar SNR. But at the same time and at the same direction, you want to limit the target's ability to eavesdrop information. So you want to limit the useful signal power that you send towards the same direction. So limit the eavesdropping SNR of the target. And of course, you want to typically would have, let's say, quality of service constraints for the communication users. And you can see how now you can formulate, let's say, these problems with these interesting conflicting constraints. There's also an opportunity when it comes to this dual functional operation, where actually typically, physical layer security, communications only security, typically benefits from knowing something about the eavesdropper. And here, if your eavesdropper is your target, the radar operation is good at estimating parameters of the target. So the radar operation here can assist the security in terms of estimating either direction of the target, so when you want to steer your nulls and do secure beamforming, or even channel parameters or SNR even of the target. And then you can apply classical, as I said, physical layer security approaches like secure beamforming, jamming, artificial noise, and so on. And here, very briefly, I'll try to go through a simple example where we've taken the same scenario and applied an artificial noise approach. So our transmit signal is the information signals, the modulated data precoded by precoding matrix W, and we add artificial noise. And the covariance matrix of my transmit signal, which is important for the radar design, is basically the sum of covariances of the beamformers and the artificial noise. And then you can define the signal to noise ratio of the communication users, the legitimate users, a function of that. I won't go into the details of the math, but it's, those of you who are familiar, it's pretty straightforward. You can also formulate the eavesdropping SNR at the target, and that's going to be a function of the beamforming and the noise covariance, artificial noise covariance. And in this work over here, that's overviewed in this paper, we use the secrecy, worst case secrecy rate. So the worst rate between pairs of target in every possible combination with user to quantify the performance. And we looked at a number of scenarios. One of the interesting ones and easier to explain is the one where we have perfect channel state information for the legitimate users and uncertainty in the target direction. So you want to, in this case, you want to form a wider beam in the uncertainty region. So make sure you're able to detect and track the target. But now that you've widened your beam, you have a wider region where you need to ensure security, basically. So your security constraint becomes a bit more demanding. And here's an example optimization where we minimize the eavesdropping SNR of the target. Subject to our radar metric here is the peak to side lobe ratio, so the quality of our beam, how large our main beam is compared to the side lobes. And here we also want to, as I said, constrain the radar beam to have a certain width so that it covers all the area, the uncertainty area of interest. And if we have an uncertainty interval of phi, this means that our 3dB beam width should cover this area. And then we have some typical constraints. So the quality of service constraints of the users, SNR, transmit power, and a number of constraints that relate to the way we present the problem. And this problem can be solved by fractional programming and semi-definite relaxation. Again, a couple only of indicative results. You can see here the resulting beam through this design. The dashed line is the case where we perfectly know the direction of the target, so we can form a very narrow beam. But as the uncertainty increases, we need to have a wider beam. So you can already see that we reduce both the radar gain, so the radar, the strength of our radar link, but also the eavesdropping, let's say, signal towards the target. And also we have a worse peak to side lobe ratio as we do that. And again, another direct trade-off where we now have the secrecy performance against the radar performance, in addition to the before trade-offs, the ones we showed before. A number of lines here representing different parameters and different uncertainty regions, but the main picture here is, again, that you can trade off from a full secrecy performance or a full radar performance and anywhere in between. And this can be done by tuning the radar, the secrecy constraints. Now, a final bit that I hope I have a couple of minutes to discuss about is this use case where we use this dual functional signaling to assist through sensing a communication scenario and demanding scenarios, basically circumventing the channel state information acquisition in a vehicular scenario. So typically, comms-only solutions you'll have to iterate. There's a feedback basically process where you iterate between beams towards the user feeds back either information, either relating to calculating its SNR or some sort of beam index that they find a better quality link. Then you can refine the beam, so make it narrower and continue this process, and so on and so forth. So you typically in your transmission block, you have a beam training stage, and then you have your data transmission. And the narrower the beam that you select, obviously the better transmission of data, the better the quality of the link, but the more overheads you need to spend in the frame. So there's again a fine trade-off in terms of the beam accuracy and the overall communication performance. Now here, radar, so sensing operation is a good thing, where you can use the echoes of your signal to basically, and direction finding, to inform where you need to beam steer. And this, through DFRC signaling, this has a number of benefits. First of all, you can remove the dedicated pilots and the dedicated channel estimation in your frame. Also, by avoiding this feedback, you save in terms of feedback errors or quantization errors, where you need to quantize your feedback to send back to the base station. And then the whole frame can be used through this DFRC signaling. You can use for both sensing and communications, so you can keep estimating the direction all the time. And that gives you a gain in the estimation performance, so the sensing performance, where once you have the whole frame, you have a better match filtering gain, and you get more accurate angle estimation. And we've used this, I won't go through the math, there's a lot of math here, but we've used this in this bit of work, where we try to estimate the direction of the user and use a simple prediction model, so a straight transition model, which has all the radar parameters we're interested in: angle, distance, velocity, cross-section. You're able to estimate all that through match filtering with the echoes. And you can use prediction, a simple Kalman filter we use here, to predict the next beam you need to form. And by the way, you can do that with the communication only case. And this is the comparison we have here. So we have a scenario where we have the base station around this, let's say, position, and you have vehicular user crossing in front of the base station. And we compare three things: what I just explained, the Kalman filtering approach with DFRC signaling, Kalman filtering approach with comms only signaling, and a beam search approach, where the communication user picks between a pair of beams and feeds back to the base station. Now you can see that all three have a certain performance that is increasing, but once you get close to the base station and the angle changes very fast, this beam search approach cannot keep up with the fast changing of the beam, so that the optimal beam can be outside the pair of beams that you want to search. Similarly, the comms only approach suffers in terms of accuracy of estimation because of the limitations in the data block, while the DFRC, with this increased match filtering gain, can keep up and in fact increase performance given the lower attenuation once you're closer to the base station. So I hope I had to wrap this up really fast, but I hope I've been able to convey to you that the spectral gains, the energy and the hardware gains that you can achieve with this dual functional signaling. I hope I convey that once you have this dual signaling, you can use one functionality to assist the other, and we saw an example of a sensing assistant communications. And I hope I managed to also highlight some unique and interesting security challenges that come with these dual functional signaling. Just one slide on what I think would be a bit of future work in this. I think there's plenty of scope in further improving, in further designing waveforms and signaling and making these more hardware informed. And there's plenty of research to do that, following research from communications only research literature. There's plenty more in this sensing assisted communication that I just showed, where early works involve simple scenarios, simple channels, so that the user is seen as a single point target, which is not really practically the case. You can have complex trajectories, many communication users, and this complicates the scenario a lot more. There's plenty of open research to be done in secure DFRC, where a number of different security solutions can be involved. And I think, towards this this vision of this smart city sensing and communications, at some point we need to think about multi-cell DFRC, how different base stations cooperate, multi-cell communications, multi-static sensing through the opportunities that we have with this common infrastructure. And with that, I think I'll end here. I'll add some references in the slides so you can take a look at the works that this presentation has been based on. And with that, I'd like to end here, and thank you very much for your attention.
Thank you very much, Christos, for a very clear, nice and wholesome talk. I think in the interest of time, we should take maybe one quick question.
Okay.
Okay, can I ask a question?
Please, yeah, Giuseppe.
Okay, so just to make sure, when you talk about these beam patterns for the radar, is this the illumination beam pattern? So is it the transmitter or the receiver? So what do you assume? Do you use like the array, so MIMO radar for the, because you can illuminate the target and then get the scatter waveform, but when you get the back scatter waveform and you want to estimate, say, angle of arrival, well, you need a vector observation and use some form of, I don't know, super resolution or whatever angle of arrival estimation.
No, I mean, at least in the first couple of works that I showed this joint waveform design, the assumption is a line of sight channel, and we want to point a beam, a transmit beam, towards the direction of the target, and we assume that we will receive the backscattered signal. We don't really focus on the estimation side of things. We go as far as designing a good beam that points, to the direction of the target. As I said, you can do many variations of that. You can employ that, bottom line performance metrics in optimizing your signaling, if that answers your question.
Yeah, well, maybe we can take it offline because it's not fully clear. Okay. And in radar, you always have these two things, like you have illumination of a wide angle or a target, and then you get you have to receive something to estimate, right? And then what you receive, it depends very much on your assumption. Like, for example, if you have an array, you get a vector. If you have only one fixed, say, one beam, well, you get some, I don't know, maybe you get a delay or a Doppler shift, but the angular resolution depends on the width of your beam. So
definitely, that's definitely true. I just want to say that in this work, at least that the one I showed, we don't really focus on the receive processing. We focus on forming a good beam, and probably, as you said, that's probably more suited for, let's say, delay and so on.
Okay.
All right, thank you very much again, Christos. I'm sure there's more questions. I can see people raising their hands, but unfortunately, I think we're gonna have to move on just to stick to the schedule. Perhaps you can type your questions in the chat, and Christos, if you're kind enough, maybe to stick around and
I'll try my best.
answer some of those. All right, cheers.